So my name is Henry Quach. I'm a second-year PhD student here at the Wyatt College of Optical Sciences at the University of Arizona. If you got here through a beautiful banner that was made by Amy, part of our college's administration, thank you for that, Amy. And thank you for all my friends and family who are joining me here today, as well as people I don't know. I would love to get you interested in optics and the science of phosphorescence and fluorescence, which is the topic of this discussion. So I want to start off with just talking about how lighting shapes our everyday life. Like, we usually don't think about it, but lighting is literally so important in everything we do. Like, when you go to a shop, people have designed the lighting so you will buy stuff. It's literally like verbiage in a lot of scientific papers that you need to design lighting so people will feel more comfortable in your store, and like you need accent lighting so that people will buy specific products, right? You want to highlight the cool functional uses of your product that you're trying to sell, as well as maybe the function is making you looking cool. That is a function in of itself. So when people think of product design, they usually think about mechanical things or electrical things. But like, they don't think about things that are very subtle enhancements to our lives. Like, one example I'm going to bring up later is that I bought this Pua from a Disney store, and he's adorable, right? But Disney has trickery afoot and has made his eyes brighter and this tattoo butt brighter as well. And I'll get into how they do that. But it probably contributed me to spending the money and giving it to the big mouse. Anyway. Lighting is huge in our perception, and I want to start off with a quick example. And we'll get to the real science just a little bit, but this is just for illustrative purposes for all backgrounds. This is a light bulb that I 3D printed. I found this on Thingiverse. It weighs about 20 grams, it's hollow, and if I shine a flashlight through it, it looks white, right? It looks really white. I'd be a jerk if I told you it wasn't white, because realistically, I have no business wasting your time and showing you something that's white that's actually white. And so of course, some trickery is afoot from myself. And so I'm going to go ahead and turn off my light. And so of course, you might see that this is actually glow in the dark. So my screen is illuminating my face right now, which is why you're able to see my face. But this is self-luminescent. This means this is a light source in itself, and light is emanating from this plastic. And there's special reasons for that, and we'll get to that. And so if I ask you what color this was, you'd be like, okay, trick question. It depends on the illumination, right? This might be green in one light. It might be red in another light. It might be white in that original light I showed you. And the specific mechanism is, it now seems relatively simple to me. I'm going to go to my light changing thing. And the way that an image is formed in our eye is that we have sources of light all around us. Rays from those sources hit an object, and some of those reflect back into our eye. Depending on the wavelength of light, let's say it's red or blue or green or violet, that's the color that you would perceive. The wavelength of the light is mapped to some perception, some perception in our mind, just the way that we are wired. And so, for example, if I change the wavelength to around 680, which is red, this is I've just cool lighting in my room. This is what I've done with this is what I do with my money. You can see that this looks a little bit more white, a little bit more red, just because red rays are reflecting and coming back. If I change it to green, right, then green, it's mostly green light in the room. And let me bring my lamp closer because it's not as convincing. So let me bring this light fixture over, and gosh, I wish I had a filter that did this a little bit better, but it's saturating. Okay, but anyway, this is green light. I'm gonna change it to purple light. I should appear a little bit more purple right now. Hopefully it does. It's not your screen, it's me. And yeah, illumination is just really important because earlier when this was glowing in the dark, it was always glowing in the dark. It wasn't like I turned it off. It's just always emanating energy. But it turns out that all the reflection of the sources in the room kind of drowned that out. And so you might not have seen that. In most cases, that wouldn't have mattered. This is glow in the dark. You would have just seen this as white. Nobody would have faulted you as calling this white. But in reality, the answer to what color is this is really perception based. And it's not dependent on just the material. It's dependent on the observer, the material, and your illumination. And so I want to take a quick detour and get a little bit into the science first, just because there's some things that are better explained with a screen. And unfortunately, I have not found the screen share function on the Facebook live share, so I'm going to share it through this iPad I have from lab. And I want to talk a little bit about the electromagnetic spectrum. I hope it appears just fine to you. Let me know in the comments if it doesn't. But the main thing is that the visible light we see around us is not the only radiation there is. We have tons of electromagnetic radiation, which is just propagating packets of energy, just flowing, circulating, bouncing, reflecting, transmitting around us. And we know a lot of these. For example, in AM radio, that's around 300 meters wavelength. FM is around 3 meters. Your Wi-Fi, your Bluetooth, and surprisingly, your microwave they're all at the same frequency. They're at about 12.5 centimeters. Visible light is between 400 and 700 nanometers, and X-rays are less than 10 nanometers. And so the big difference, if you can see in this chart, is that you see this kind of this sinusoidal wave going in one direction from the FM, the AM side to this radioactive side. And as you get to smaller and smaller wavelengths, those contain more and more energy. So in the visible spectrum part of this diagram, you might see that, we go from red to purple in, the more energy direction. So we know that purple has more energy than red, purple has more energy than blue, than green, than yellow, than orange, and the like. And so that's going to become a really important detail for us. You need to know that every time you see a red object, red wavelengths are what are hitting your eye and you're interpreting that. Like, for example, I like 3D printing. I 3D print a lot of stuff, and a lot of the demos I have are 3D printed. I printed this baby little sheep. It's orange, and a mix of colors causes you to perceive orange coming to your eyes. Okay, so we're going with next is the reason why we call things certain colors, and if I call a fire truck red or a frog green or the ocean blue, you wouldn't fault me, right? It's because we're so used to white light. We evolved our eyes under the illumination of the sun, in which white light is a huge part of that, and it happens to be that white visible light, as we know it, 400 to 700 nanometers, gets through water just fine, which is probably evolutionarily advantageous for our ancestors. But there's more than that. There's light we can't see, right? I know that's very similar to a book title. This presentation does not endorse the book, but for example, I have a special light source right here called a black light, and it's not exactly black, and I'll explain why. But when I turn it on, it'll appear purple to you because this is centered on the part of the spectrum that is ultraviolet. And so the purple that you see here is just kind of extra stuff on the tail end. That's not the main source of power in this light. The main source of power is in the ultraviolet, which we can't see with our own eyes, but you just kind of have to believe me that the majority of this is in a spectrum that we can't directly see. And so, of course, this has more energy. There's more energy than the regular centered purple wavelengths, maybe at 400 nanometers. And we can do some fun stuff with this. Like, for example, let's do some stuff in the dark now. Let's do some glow in the dark stuff, and I'll show you some that I've 3D printed. So turning off my lights. If you are a Futurama fan, this is something I made in SolidWorks. This is something called The Scary Door, right? It's a show within a show. Anyway, if I expose this to ultraviolet light, this material is very special, and it's going to absorb all of this energy. And now, right now, you should see that it's kind of bright, right? I'm going to turn off my screen and hope that it looks even brighter. Okay, so hopefully this should appear pretty bright to you. Yeah. And in addition to that, I made this OSC logo. So this is glow in the dark, right? Cute, right? You can see there's just no white light around, so there's no reflection from any sources in here. It's just the UV light shining on this. And now I'm going to turn off the UV light. Even without the UV light, this still glows pretty well, just because, you know, energy is coming from it. So turning back on my screen, I want to show you exactly why this happens. Where are my lights? So back to the iPad, because I have no other way to show you. This is called phosphorescence. So anything you know is glow in the dark is probably phosphorescence. If you ever grew up with glow in the dark moons and stars in your children's bedroom, this is probably what's been happening. And specifically, this special material, this is just plastic, by the way, and a lot of these plastic little toys, it's just regular plastic with a phosphor added in. So a phosphor is just a material that absorbs a wavelength and emits another. This happens all around us. It's very useful in many ways. And in this specific case, for 3D printed plastics, we use something called strontium aluminate. So it's a heavy metal bonded with the plastic that, you know, makes up this material. And this specific material absorbs energy and then converts it, and then loses some of the energy, and the rest of it is emitted as light. So in this diagram, the blue is all the absorption, right? So we start from when light hits matter, that energy from the light is absorbed into an electron in the matter. Oh, here's the way I'm facing, right? And it goes up to an excited state, right? And so shortly after that, it degrades a little bit. It falls into a secondary state right here and loses a little bit of that energy. Loses a little bit of that energy to heat, and that's just vibrations in the lattice if you've taken some more optics classes. And with the rest of that energy, it emits very, very slowly over time and just releases green wavelengths, just these packets of energy. And so what really matters is that, let's say if you absorbed a certain wavelength, let's say you absorb blue, that means you could possibly later emit green or maybe a wavelength with lower color. It would never make sense if you absorb blue and then emitted purple, just because that means you violated the conservation of energy, and you deserve a Nobel Prize if you actually made it happen. But we'll see about that. And some demo I want to do to show you, to convince you that maybe glow in the dark stuff you can only down convert the wavelengths of light, right? Like right here, I've been exposing this to ultraviolet light, in which I've told you it contains more energy than regular visible light, right? Maybe if I exposed it to this white light, you could see plausibly this glow. But what if I expose this to red light, right? Would it glow? I can show you real quick. So with my special lights and this spool of 3D printing plastic, let me turn off the lights, because we're going to conduct a real experiment. We are people of science and the empirical method. If I turn off the lights, hopefully you won't be able to see much of a glow, right? The glow should not be very obvious. I hope that there's not any obvious glow. And I'm going to immediately turn on my lights to be red. And this is this illumination you should have seen earlier. I call this one Charmander, right? So it's just the lighting scene in my Philips Hue app. And I'm exposing it to this red light right now. Let's give it a couple seconds of exposure, right? Couple seconds, and now I'm going to turn off the lights, and we'll see if you see any extra glowing. And you should see there should not be any extra glowing, right? No extra glowing. And if I expose this filament to a different color, let's say green, right? Let's try again. I call this one a Bulbasaur because green. And would you expect it to glow green or not? Well, maybe you might think it might glow green later and absorb the energy, but remember that you need to absorb a higher wavelength of light to emit the one that you want. So you want to emit green, you need something with more energy than just green wavelengths, right? So I'm going to shine this a little bit with green, Ugh. And then I'm going to turn off the lights. So turn off the lights, from my view, it doesn't look like anything's happened, right? Nothing's, it's only absorbed green. It cannot make the down conversion because there was no higher amount of energy incident on this material to start with. And finally, sorry, just, I can't tell who's in the dark, and I'm always in the dark in this scenario, so it's really weird. I'm just talking to a webcam. I'm gonna go to this mix of blue and purple, and I call this setting the PhD written qualifying exam. I'm gonna shine it a bit with purple. Hopefully you can see purple, or at least my face is purple, but I'm just shining purple on this. And I'm gonna turn off my lights and lights off. Please, internet. Wow, bad time for my internet to freeze. 1 second, technical difficulties. Okay, so hopefully now, hold up, let me turn off the screen again. You should be able to see now that this glows a little bit, right? Hopefully you see it glows a little bit. And that's because the purple light that I exposed it to, this material was able to down convert all of that energy into a lower wavelength and emit that. So you saw for that the red and the green, it was unable to do that. So hopefully that was a helpful demo. For example, some more fun stuff I want to show you just because I can, and because I printed it. I ended up printing this little nice plate. And so I'm going to turn off my lights again. And to help you remember, I made this little phosphorescence card. Now I don't know where the focus of my camera is, but I hope it's in focus at least once as I'm sweeping this, right? Phosphorescence, right? And I even got some of these things made. I got these little widgets that glow in the dark. I've got stars. I've got the ISS. I've got the Hubble. I've got a spaceship. And yeah, I don't know. I think that's really cool. That's literally how glow in the dark works. You have material that absorbs one wavelength and converts it down to another. Now, the really cool part of this is in fluorescence. Fluorescence is a thing that's actually everywhere. So for fluorescence, we really need this right now. Fluorescence is different from phosphorescence because instead of converting down in 2 steps and losing a little bit of energy on the way, it's converted down in 1 step. So when a photon or light energy is absorbed, it, instead of going down like this, it goes down directly in 1 step right here. So right here, we absorb, and this happens so fast. It happens in like a nanosecond, while the other phenomena, phosphorescence, happens in like thousandths or 10,000ths of a second, which is pretty slow for light standards or visible light standards. And this is the part that is everywhere. This is the part where it's embedded into product design. You can put your tinfoil hats and know that the companies are manipulating you to buy stuff because it looks brighter, more radiant than it should be. When people are saying, oh my gosh, you look glowing today, you look radiant, right? This is kind of what they're talking about. Sometimes they put fluorescent compounds into your moisturizer or your skin cream. They literally do that, okay? And so let's get into this. One example of things that fluoresce, in which, of course, it's the same kind of down conversion mechanism. You absorb light, you emit a lower wavelength of light. You don't get all of it. That's just part of absorption. You will always lose some of it to heat. One of it is in highlighters. So, for example, if I can find my highlighter on my desk. Oh no. Oh gosh, where'd it go? Where'd it go? I don't have my highlighter. But literally, highlighters use some of this fluorescent dye in order to make your stuff look more bright. Oh, I found it. So, for example, on this piece of paper, right, if I were to highlight it right now, if I were to highlight it, turn on my UV light, and turn off my regular lights, you might see it has like a very ghastly glow, right? And it glows a little bit more just because it converts some of the UV light, which is from this lamp, into visible wavelengths. The primary part of this is that the part of the design is that in order to make highlighter ink look more, well, kind of bring out the parts of text you want to bring out more than other text, is that you use some of the UV light in the room. So let's say some of your incandescents have a little bit of the UV spectrum, or maybe you're in sunlight, right? It converts some of that UV light, which you can't see with your regular eyes, well, always regular eyes, and then converts into visible light, which comes back to you. And so it looks a little bit brighter. And Jaron asked a question, I'll get to that if I can. And so yeah, highlighters is one huge thing that uses this tricky technology. Another thing that uses tricky technology that seems kind of mundane is mail, right? So actually, let's not get to mail first. Let's just talk about regular paper, because you see this is kind of blue. This is actually fluorescing. Regular white paper, copy paper, most paper you handle every day, it fluoresces. When you make paper, you put it into a pulp, and there's this kind of cell wall structural component called lignin. And lignin is a very yellowish component, and naturally, when you make paper, if you were to add nothing to it, it would look very yellow or brown, right? If you chop down a tree and try to make paper, right, but by some primitive technology kind of methodology, you would not get anything that looks white like this. This is all very artificially induced. And so they add something called OBAs, or optical brightening agents, where these chemicals fluoresce under ultraviolet light. And so that's why when I put this ultraviolet light up against this, the ultraviolet light is converted down to blue, and the blue kind of offsets the yellowishness of the regular natural paper. And apparently this is a really, really big deal. You know, on most copy paper that you have, if you were to put against the wall and just let it sit there over time, it would degrade back to the regular yellowish tint. And you might see that for some stuff that you've hung up in your room. And so where people really get antsy about this is postcards. If you look at hipster postcards online, a lot of them will brag about not adding OBAs to their paper, because when you write a nice hand-lettered note to your friend, you mail it off to them, as good friends do, and you hang it up, you don't want that to fade over time. You want it to preserve the appearance that it had when you first made it. And artists are really into this. They pay a lot of attention to the canvases that they have, the paper that they do their art on, because if they hang it up and put it in a museum, well, if the museum is lit badly, and let's say there's a lot of UV light or a lot of sunlight, well, the appearance of your painting or artwork might fade over time. So there's whole chapters of books just on museum lighting where they filter out the UV. And, you know, famously, there were a lot of internet articles a couple years ago about, you know, flash photography is banned at the Louvre, and it's part of that, you know. These days, they have frames with special glass that filter out the UVs. They just make the paper in the medium without UV. And they even just put UV filters over our camera flash modules. Yeah. So in addition to making things look more bright, actually, let's get into this. Let me show you Pua, right? I want to show you Pua under ultraviolet light and how he's tricking you. So this is Pua, and this is Pua next to ultraviolet light. How do I orient this? Okay. All right, we're gonna do this step by step. We have him over here, looking at you, the viewer, and I'm gonna have this. And you should see that his pearly white eyes get brighter than the rest of his body. That's because his eyes fluoresce. Textiles, all the laundry we have, a lot of them have these optical brightening agents, or they call them fluorescent whitening agents, FWAs for textiles. So I purposely wore a non-FWA shirt today, just so it wouldn't fluoresce and you wouldn't see all the detergent stuff. But to show you that detergent literally has FWAs, I poured some of my own detergent out, and you see that it glows blue under this light. So yeah, Cool, isn't it? Like just adding this to your laundry will make it brighter because of this chemical in which the FWA absorbs the ultraviolet light and down converts it to blue to offset the yellowness of the textile. So naturally, cotton is more yellowish than pure white, although our standards have kind of gone up for pure white over time, just because we're just so used to these OVAs and FWAs being added to everything. And even in advertising, right? Like, check out my toothpaste, right? Like this stuff fluoresces too. Any bluish sheen you see on this is just due to fluorescence. And there's so many other things. Actually, sorry, I forgot his butt tattoo. Yeah, he got branded by Disney, and you can like totally see that they want you to know he was branded by Disney. Look at him. Oh my gosh. It's like Iron Man. Look at that. Anyway, functional uses now. They use this for tagging money, which you might know. Kelsey Cronin had a presentation recently in which she showed some of the infrared features of a dollar bill. But for any denomination you get above, let's see if we can do this right. Maybe. Let me turn off this light because the contrast needs to be better. Hopefully you can see that at some point in the sweeping range that there's a fluorescent white, there's a fluorescent stripe. So not all fluorescent dyes are made equal, and different dyes will respond to different sources of light in different ways. So getting this fluorescent dye is apparently a very hard thing in counterfeiting. And some criminals, some people who do counterfeiting, they apparently try to make money out of, maybe more common material like regular white paper that does fluoresce, right? And so if I had a counterfeit bill, it could entirely fluoresce under the light as well. So that's just one way of detecting counterfeiting. But money's not the end of it. Your mail is part of it, right? Like I don't know if you can see this clearly, but you should be able to see this this stripe on here. There's this yellow stripe on this stamp that one of my friends sent me, and this is used in postage stamp tagging. So postage stamp tagging is just an automated process in which if you've mailed in something, it's going to put a marker on here so that the automatic processor machine can align it and sort mail faster and more efficiently. And so, a lot of people say that, this is used for tagging, making sure that you've canceled your stamp. And for those of you who are not familiar with stamp collecting, I wasn't until I started researching this. Stamp cancellation was a method of just marking a stamp to show that it had been used. And so you can't save 45 cents on your next letter to a friend. So I hope that showed through, but there should have been a yellow stripe that showed on here. And these days, I've checked a lot of my mail. Some of them have this mark, some of them don't. But all the handwritten ones actually have another fluorescent marking. And I don't know if you can see it, but there's this orange barcode right here. I hope it's not saturating. I hope I get it at some point. But there's this barcode where if you hand wrote the address, what the USPS will do is they'll take a picture and they'll associate it with this information tag so that when someone eventually goes and reads your stuff, they can just re-reference this easily. And the reason why they make it fluorescent is because, it's kind of designed for functionality. If you have envelopes that comes in all shapes and sizes and colors, if you get something with a pattern and envelope, right? How is the machine going to use machine vision to distinguish the barcode from maybe a black barcode from maybe a black design, right? You can't. So they use a fluorescent ink and a special illumination scheme under the UV in order to see these barcodes. So I don't know. I thought that was something cool that was present in fluorescence everyday life, but might not be apparent. Something that might be brought up about this is that, what about bioluminescence, right? Bioluminescence, you might associate with jellyfish, or if you're familiar with the biomedical sciences and jellyfish, that some proteins or some things that you want to track through a cell system, you want to see. So example, if you want to track a virus propagating through a toast, you might attach a fluorescent protein, it's actually from jellyfish, to this, and then just shine a light on ultraviolet to blue light on your entire host infected with the virus, and watch as the virus propagates through. So if you're testing new medicines and watching different things go through the liquid, you're probably using what is called GFPs, or green fluorescent proteins, in which a Nobel Prize was won for this, in which they discovered this natural bioluminescent protein, which converts a higher wavelength to a lower one, ultraviolet or blue down to green, makes a great effect for seeing things that you wouldn't be able to in regular white light. Yeah, but that's what I have for you. If you heard of any news about glowing rabbits, glowing sheep, it is definitely bioluminescence, and it's probably GFPs or green fluorescent proteins. And again, the main thing I wanted to go over was that light comes in all sorts of wavelengths. It oscillates at different rates. And for that reason, some of them have more energy, and some of that can be absorbed and down converted into colors that we can't see with our eyes. It's pretty cool. A lot of the stuff in your room is fluorescent just because these dyes are now so cheap. It is noted that because these are so cheap and glow under fluorescent lighting, you can actually track pollution with this. So sometimes people go into rivers and lakes and sewage systems with ultraviolet light. And because of all the plastic which contain these optical brighteners, and textiles thrown away that contain these optical brighteners, and paper and even toilet paper is fluorescing these days, you can see where the highest densities of pollutants are and where trash has been thrown, which is super cool use of just ultraviolet illumination with natural material properties. And then, yeah, next time you go into a store, I hope you maybe think about this, and like if optical brightening agents have been added, or if the paper you choose will detract from the sentimentality of the letters you send to friends years from now. But yeah, that's all I have. I'll take questions. Hope you enjoyed this. Hope it wasn't too long. Hope you learned something. As for Darren, my answer to your question is I actually do not know the reasons why fluorescence and phosphorescence got their name. I see that Hyungmo has said that phosphorescence comes from phosphor, and that is due to chemiluminescence, just because of the physical quantum nature of phosphorus. But I think most of these days, the optical brightening agents do not actually contain the real element phosphorus. They're just different things that fluoresce or glow. But yeah, that's all I got for you. Take some more questions. A lot of this stuff was really interesting. Like, for example, did you know a lot of double-sided tape is fluorescent itself? So in the example I had with the little space stations and stuff, if I turn off the lights again, maybe you could have seen a flash of it, but you might see blue stuff right here, and that's the double-sided tape I have used. The reason is because it's probably of their interest to have adhesive on both sides rather than the one. You don't want a customer angry because they only got one-sided, double-sided tape. And so they put this fluorescent compound inside one side of the tape to make sure that it got on. And there's probably some UV system where they track whether you can see blue or not fluorescing from this tape. So I found that by mistake. I was literally just waving this black light wand around my house and just trying to see where I could find that fluoresce. And this was one of the cool things that did. And I looked it up, and there wasn't a lot of commentary about that, but there was a patent. So cool stuff. Yeah, that's all I got. All I got. If you have any questions, I'll stay on for at least 2 minutes, and then, or maybe longer than that, and then bid you adieu. I'll just talk about other fun stuff I found in the blacklight in the meantime. Also, a word of caution about these blacklights: if you do end up buying one, because they are kind of relatively affordable and they look really cool for cosmic bowling and concerts and stuff, make sure you get one that's not in the UVB or UVC range. So this is a UVA light, which means that its spectrum only goes down to, I think, 320 nanometers, which is not immediately dangerous to humans, but I might correct myself in the comments. UVB and UVC is what we associate with the sun, and that's what gives us sunburns. And you certainly do not want to buy this from a terrible manufacturer and be giving yourself unhealthy doses of radiation. So if you do end up buying these, and these are affordable, you might be able to find things that fluoresce that you didn't think would. For example, you think that companies that want really pristine looking products, such as Apple, right? They're all about like brightness and crispness. Surprisingly, iPad plastic does not fluoresce, which is good on them. I think the company would not like their products to fade over time and look like a less sharp product. All my 3D printing plastic, all my white 3D printing plastic turns out to be fluorescent, just because if you didn't know, for this typical plastic that you have, most of the plastic actually starts out transparent, and you have to add in pigment or dye in order to have a color. So all of this white that was added in, all of it is fluorescent because it's probably cheap at this point, and it might be a manufacturer default. So maybe by design or maybe by cheapness, that's what happened. That's why a lot of things fluoresce. And I'd probably go with the cheapness aspect. I'm not sure if they cared as much about these fading over time, because a lot of these things are consumables, right? You eat from plastic and you might throw it away. And in a similar vein to why this fluoresces, and why manufacturers don't tend to want this to just be all natural and not fluoresce and maybe a little bit less white. The glow-in-the-dark stuff, the reason why they chose this glow-in-the-dark stuff is because, well, it's cheap and it's non-toxic, and non-toxic means, well, it means it's cheaper than it could have been, if you know what I'm getting at. And as well as that, it emits green, in which we've evolved to see green the best, and so we have the highest spectral response to green. And so this just happens to be one of the best ways in order to get light into your eye from self-luminescent sources. Well, that's it. I don't see any questions. Thank you for joining me. Hope you enjoyed the demos, learned something new. Think about this next time you go shopping. Hope you are all safe and healthy. Have a good day.